are going to see two lemmas. The first of which is this. Let X be a set and B be a basis for a topology tau on X. That means X actually is the topological space with topology tau which has this B as a basis. Then the topology tau equals the collection of all unions of elements of B. That means if you collect all possible unions of elements coming from B, then that collection will equal tau. So let's prove this. So the proof starts like this. In the beginning itself we notice that the basis itself is a subcollection of tau. We already know that the basis elements themselves are also open sets, so they are in tau. And because of this, any union of elements of B is in tau. But exactly how? Any union of elements of B involves the union of the elements of some subcollection of B. Let B prime be one such subcollection. Then if that's the case, then B prime is also contained in tau because B is contained in tau, and as such for any element U in B prime, U is also in tau. So if you now take the union of such U's, then obviously it will also be in tau because tau is a topology. That is why any union of elements of B is in tau, like this union is in tau. Next we want to prove that any element in tau is equal to one such union. So in this second half of the proof we take any element V in tau. And now let us consider any point X in V. For any such point, there exists a basis element Bx in B which contains X and is itself contained in that open set. Why? Because that's what basis does. Okay. And then what we see? Then we see this. That V then will have to equal the union of all such basis elements Bx. But how is this equality coming? You note one thing, that no matter what X we are choosing from V, that corresponding basis element Bx that we are getting is a subset of V. So all the Bx's are subsets of V. So obviously their union would also be a subset of V. So this is a subset of V. Conversely, you take any element in V, say X in V, then X belongs to this union because X belongs to Bx, one of the sets in this union. So any element here is also in this union. So this is also a subset of this, and as such they are equal. So we have expressed any open set in tau as a union of basis elements. Okay. So not only are such unions elements in tau, but every element in tau is of that form, is such a union. So that proves this lemma. So far we have seen our journey from a basis to the topology that the basis generates. But now in this next lemma, we go in the opposite direction. A topology is given to us on a set and we want to create a basis for that topology. So let's see the statement of the lemma. Let X be a topological space. That means already there is a topology on X. And let C be a collection of open sets in X. That means this C is a sub-collection of the topology. It's a subset of the topology, whatever topology is there in the background. With this property, such that for each open set U in X, that means for each element U in that topology, and each point X in U, there exists an element C in this collection C, such that X belongs to this C and this C is contained in U. This looks just like the definition of the topology generated by a basis. Then if this is true, then that collection C is a basis for that topology on X, which X already has. So let's now prove this. For convenience, we start the proof by naming the topology that X has. Let us call it tau. Let tau be the topology on X. We do so because we don't want to again and again write the topology on X. We can just write tau. Now we have to prove that the collection C is a basis for tau, and there are two things for us here to show. The first is that C is a basis for some topology on X, and the second thing is that that topology is actually just tau, nothing else. So in this next paragraph, we first show that C is a basis, and then we go to the second part. So let's go one by one for the conditions that a basis has to satisfy. The first is that any point X in X has to be contained in some basis element. So let X be any point in X. Now note that tau being a topology contains the set X itself as an element. So by the property that this collection satisfies, there will be a set C in this collection such that X belongs to C and C is contained in that set X, in that open set X. Now this part I have written in brackets because it's not really that important here. We need only this much. So this argument shows that yes, indeed, any point X in X is contained in some set from the collection. So the first condition for a basis is true for the collection C. For the second condition, we take two elements C1 and C2 in the collection C, and we take a point X in their intersection. Now note that the collection C is a subcollection of tau. Why? Because recall that C originally is given to be a collection of open sets. That means anything that we have in C is ultimately coming from tau. So we have this containment, and that is why these two elements of C are also there in the topology. That means C1 and C2 are open sets in X. So their intersection is also an open set. Finite intersections of open sets are open. So the intersection also belongs to tau. Now what is happening? Now you concentrate on this intersection. This intersection is an open set in X and it contains a point X. So by the property that the collection C satisfies, again just like this one, there exists a set C3 in the collection C which contains X and which is contained in this open set. But then this is precisely what you need for the second condition for a basis to be true. So the second condition is also true for our collection. So the collection C really is a basis for some topology. So in the next part we will prove that that topology is nothing but tau. So we write the conclusion here, hence the collection C is a basis for some topology on X, and let C generate the topology tau prime on X. Let the topology be tau prime. Now with the next part of the proof, we want to prove that tau prime is equal to tau. So let us take an open set U in tau. Then for any X belonging to U, there exists, you see, in this part we are using the property that the collection C originally has. Not that it's a basis, okay, that's not the part we are using here, although just now we have proved that the collection C is the basis. But the original property that is given in the statement of the lemma, that's what we are using here. Because we have an open set U in tau and a point X in U, so there exists a set C in the collection C such that X belongs to C and C is contained in U. But then, now after writing this, you use the fact that C actually is a basis and it generates the topology tau prime. And because of this line, U becomes an open set in tau prime. Why? Because that is the definition of the topology tau prime which is generated by the basis, that collection C. that if you have a subset, you see, U is open in tau, fine, but we want to prove that U is open in tau prime. Basically, U is a subset of X, right? So if you take any point X in U and you are getting the fact that there exists a basis element, okay, now you can view this C as a basis element which contains X and which is itself contained in that subset U. So by the definition of the topology generated by the collection C, U will now be open in this topology. That means U will belong to tau prime. So any element in tau is also in tau prime. So that's how tau is contained in tau prime, or tau is coarser than tau prime. We can use that term also. Conversely, we take any open set V in tau prime, and then we invoke the previous lemma, which tells us that open sets are just unions of basis elements. So by lemma 13.1, there exists a subcollection D of that collection C, so that if we take the union of the elements of that subcollection, that is equal to this open set V. And then there is a little more that will give us the proof. And the last part is this. Because D is contained in C, which itself is contained in tau. Why? Because it's given in the original statement that C is a collection of open sets in the topological space. So this collection C is contained in tau. So that is why D itself is contained in tau. This means that any W that here you are choosing from D ultimately is open in tau, ultimately is an element of tau. And because tau is a topology and is closed under the formation of arbitrary unions, so this union is a union of elements W in tau. So the union will also be an element of tau, and that's how V belongs to tau. So in this part, any element V in tau prime is also in tau. So tau prime is also coarser than tau, and that is why they two are equal. So that's the proof. So there are other things also after this, of course, which we will see next week on the same day. So see you next week with more things on topology. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.